What are space and time, really? And do they flow in the same way for every being in the universe? If you stand on Earth, does one passing second truly equal a second at the edge of a black hole? We live inside the universe. Yet do we genuinely understand the structure we move through with every single moment? Today's story invites you into a slow, unhurried journey, where the great questions are opened within the deep silence of cosmic space. If curiosity stirs within you, feel free to leave a comment, press like, share the video, and subscribe to the channel to walk with us over the long term, and to join our community of faith and contemplation. Now, take a gentle breath, let your body soften, and prepare yourself to step into the sections that follow. About 100 trillion years from now, in a future so remote that it stands at the far horizon of cosmic history, we picture a worn civilization gathered around a single, solitary black hole. The bright age of galaxies lies far behind them. The last, longest-lived stars have burned through their fuel, faded, and gone dark. The universe that surrounds this civilization is no longer a place of crowded constellations, but a vast, dim expanse where almost all of the familiar lights have already had their moment. They have chosen to stay here, anchored to this quiet region of curved space-time, to stretch out their remaining span of existence while the wider cosmos continues to thin and cool. If we look up with them from the surface of their constructed shell, the sky has changed in a way our present minds can barely grasp. There is no glowing river of the Milky Way, no dense band of stars threaded across the night. Galaxies that once filled the darkness with structure have either faded beyond detectability or slipped so far away with the expansion of space that their light no longer reaches this place. What remains is mostly a deep, almost uniform darkness, with only rare points of light still visible, and a very faint background glow that has cooled to long, low-energy wavelengths. The universe has aged from a hot, dense beginning to this sparse, low-energy era, and the direction of time can be read in that change. In earlier aeons, long before this late chapter, the same civilization moved through a very different cosmos. Back then, stars were still plentiful, and energy sources were easier to tap. They learned to operate entire planetary systems as if they were components in an immense machine. Planets and smaller bodies were dismantled and turned into raw material. Around many stars, orbits that once carried natural worlds became filled with artificial rings, swarms, and shells. Vast constructions encircled suns to capture their light almost completely, approaching the kind of power use that we imagine when we speak of advanced Kardashev-type societies. From a distance, those systems would have looked like intricate sculptures of orbiting structures, each piece reflecting and redirecting starlight, carrying habitats, data stores, and the infrastructure of a culture that had spread confidently across interstellar space. Within those networks, matter was reshaped, energy routed, and information exchanged across enormous distances. For a time, it might have seemed as if there were no real limits to what could be built, as long as there were stars to feed those constructions. Yet even this reach could not rewrite the basic tendencies of the universe. Stars still aged. Nuclear fuel in their cores was still finite. The expansion of space still carried distant galaxies farther apart, driven by the same underlying cosmological parameters. As the cosmos moved further along its one-way trajectory, the signs of decline became harder to ignore. Star formation slowed and then nearly stopped. Old stars cooled, or flared in final outbursts and then left behind remnants. The background radiation that once filled all of space with a bright, hot glow had already cooled into the microwave band and then continued sliding toward longer wavelengths, losing energy as space stretched. Entropy, the quantity that tracks how energy spreads and becomes less available for work, kept increasing. Over time, the difference between hot and cold regions diminished, and the universe as a whole moved toward a more uniform, near-equilibrium state. Faced with that long trend, the civilization looked for a different strategy, one that did not rely on youthful stars. They turned their attention to black holes, regions where so much mass has been concentrated that space-time curves extremely strongly and not even light can escape from within a certain boundary. Among the many black holes left behind by long-gone massive stars and merged galaxies, they searched for an object both massive and relatively isolated, one that would survive longer than almost any other structure. Eventually, they found a lonely black hole drifting in a sparse region of intergalactic space, far from the crowded centers where interactions were still common. Around this dark center, they built their final home, using the remnants of dismantled planets, asteroids, and the debris of their earlier megastructures. They assembled a thin shell surrounding the black hole. It was, in a sense, an inverted version of the familiar idea of enclosing a star. Instead of capturing radiant energy pouring outward from a bright surface, this shell held its position above a region of inward pull. The structure needed to be carefully balanced. Too far inward, and the material would cross the event horizon. Too far outward, and it would no longer sit in the region where the effects they sought were strongest. For those living on or within this shell, the black hole itself was never seen directly. It revealed its presence through its influence. Light passing near it was bent, forming arcs and rings. Matter falling inward heated and radiated before crossing the horizon. The shell's supports constantly adjusted to maintain orbit against the strong gravity, compensating for any small drift. In their instruments, the black hole appeared as a central absence surrounded by a complex pattern of curved trajectories and redshifted light. What had once been regarded mainly as an engine of destruction now served as the gravitational heart of their last refuge. This structure also functioned as their final power plant. The outer surfaces of the shell collected whatever energy still flowed through the surrounding space. Faint starlight from the very last. Dim suns that had not yet gone completely dark still arrived from scattered corners. The stretched-out glow of the cosmic background, now at extremely low temperatures, still carried a tiny amount of usable energy, matter, in the form of dust, gas, and occasional larger objects, slowly drifted inward and could be guided toward the black hole, radiating heat and light as it fell. Every photon that crossed their collection area was counted, transformed, and routed into the systems that supported awareness and structure inside the shell. In the language of thermodynamics, they were operating in a world where almost all easy energy had been spent. The large temperature differences that once powered stars, weather, and chemical processes were mostly gone. What remained were small gradients and the mass energy stored in compact objects. The shell turned those final gradients into a way to continue existing a little longer before the universe settled even further toward uniformity. There is no need for us to trace every step of the mechanisms involved. It is enough to notice that, at this stage, every bit of free energy was carefully preserved and used. There was another, more subtle reason for choosing a home so close to a black hole. In Einstein's general relativity, gravity is not simply a force pulling on objects. It is a curvature in space-time itself. Clocks placed in stronger gravitational fields tick more slowly compared to clocks far away in weaker fields. Time, in that sense, does not pass at a single universal rate for everyone. It depends on where you are and how you move. Near the shell, close to the black hole but still outside its event horizon, this effect becomes significant. The proper time experienced by inhabitants on the shell runs more slowly than the time experienced by a distant observer in low gravity. If we imagine 2 points of view, one tied to the shell and one very far away in a more dilute region of space, the difference becomes clear. On the shell, daily life is arranged around local intervals, cycles of activity, rest, maintenance, and reflection, all measured by their own instruments. Meanwhile, as those same intervals pass, the universe at large continues to evolve. From the distant perspective, entire eras may elapse, while, on the shell, only a shorter span is recorded. In effect, by choosing to live in a deep gravitational well, the civilization has arranged for its own experience of time to be stretched relative to the external cosmos. Seen from their vantage point, the outside universe appears to move through its remaining changes more quickly. Remaining stars in other regions fade from visibility. Galaxies still within view drift farther apart as space continues to expand. Black holes in distant clusters gradually lose mass over enormous periods through quantum processes, radiating away energy until they, too, disappear. Radiation levels fall even closer to equilibrium. The entire timeline of the universe's far future, from the end of star formation to the approach of a heat-death-like state, unfolds faster relative to their slowed clocks than it would for an observer in a weaker gravitational field. We can think of their choice as a kind of quiet negotiation with time. They have not stopped the increase of entropy. They have not reversed the broad direction of cosmic history. Instead, they have placed themselves in a region of space-time where local time runs more slowly, allowing their sequence of moments to stretch across a larger portion of the universe's remaining story. The black hole, once feared as a final endpoint for matter and light, becomes a tool, shaping not only the paths of particles, but the rate at which experiences can unfold. Inside the shell, life in whatever form it now takes continues in the glow of the harvested energy and under the influence of a clock that ticks at its own pace. Outside, the universe keeps aging, expanding, and smoothing out. Somewhere between these two perspectives, the question of what time actually is remains present, not as a puzzle demanding a solution, but as a quiet thread that connects their last refuge to the entire arc of cosmic change. As the background grows ever thinner and colder, the image of this final civilization, suspended above a solitary black hole at the end of a very long timeline, stays with us and accompanies us further into our exploration of space, time, and the structures that link them. To understand space and time as they shape that distant future, we drift backward through history, arriving in a much earlier age, when the universe was mapped not with equations but with ideas and stories, and when the first outlines of relativity were still only a faint suggestion in human thought. In the world of ancient Greece, philosophers looked around at the shifting theater of change and tried to understand what kind of place all of this change occurs in. Plato imagined space as something like a cradle, a receptacle that holds every object and every event, yet does not itself carry color, texture, or flavor. Things appear and disappear within it, transform and move, but the background that hosts them remains hard to describe. Aristotle, thinking along related lines, argued that a completely empty void could not really exist. For him, the world was full of substance and qualities. The idea of a region with no matter, no air, no properties at all felt more like an abstraction than a genuine part of nature. If we picture their view, space becomes a kind of invisible fabric stretched underneath everything, a stage that cannot be cleared away even when the props and actors are removed. A cup, a stone, a person are placed in different positions. Yet the somewhere in which they reside is not treated as a physical object, not something one can scoop up or contain. They were comfortable talking about space because it is unavoidable in experience. Yet, if they tried to treat it as a concrete thing, it slipped away from their definitions. This early tension space, as obvious and yet strangely elusive, would echo through centuries of debate. We do not need to pin down their terminology with precision. Many generations later, in the 17th century, a new style of thinking began to crystallize in Europe. The sky was being observed through early telescopes, falling objects were timed with improved instruments, and a different language started to dominate descriptions of nature. The language of mathematics. Stories about gods moving the heavens, or spirits guiding winds and storms, were gradually set aside in favor of measured quantities, repeatable experiments, and laws that could be expressed as formulas. Circles on the sky became orbits with calculable periods, arcs and chords turned into angles and velocities, and the shapes of trajectories could be plotted on diagrams instead of retold as myths. In this environment, space and time themselves began to be treated as coordinates on a kind of invisible grid. Instead of asking only what space means philosophically, thinkers now asked how to write equations that use position and duration to predict what will happen next. The shift did not erase the older questions, but it wrapped them in a new frame. If space is where things are, and time is the order in which they occur, Then a successful physical theory has to say, in that shared language, how positions and moments relate to each other. Amid this change in viewpoint, Galileo Galilei introduced an image that still shapes how we understand motion. He asked us to imagine a ship, large and sturdy, with a closed cabin below deck. Inside that cabin, plates, cups, and tools hang from hooks or rest on tables. A small tank holds water and a few fish. A bird lives in a cage. Insects flit about the room. The walls have no windows, no cracks, no portholes. From within this sealed space, no one can see out to the sea or sky. Galileo invites us to consider three situations. In one, the ship rests quietly in a harbor. In another, it rolls and pitches on rough waves, surging and slowing as gusts of wind push against its sails. In a third, it glides across a calm ocean, moving forward at a steady, unchanging speed. In the harbor, the objects in the cabin behave as we expect. Plates stay on tables, water in the tank remains level, the bird hovers or lands at will, the insects fly in any direction without particular difficulty. In the storm, the picture changes. Loose items slide, water splashes, the bird struggles to keep its balance, and the insects are thrown about by the sudden jolts. The third case is the surprising one. When the ship moves with constant velocity over smooth water, Galileo points out that the cabin, and everything in it, behaves just as it did in the still harbor. A dropped plate falls straight down to the floor beneath it, not to the back of the room. The fish swim as before. The bird flies from one end of the cabin to the other without noticing any bias. The insects trace their paths in the air without being swept backward. If we restrict ourselves strictly to observations inside this closed space, no experiment will reveal whether the ship is at rest or moving steadily. From this thought experiment, Galileo drew a conclusion that now feels familiar. There is no special absolute state of rest in uniform, straight-line motion. Instead, motion is relative to a chosen frame of reference. Inside the cabin, it is perfectly valid to say that the room is at rest and that the sea moves past outside, even though from the shore, an observer would say that the ship moves and the water is approximately still. Both descriptions are consistent within their own frames. There is no unique, privileged viewpoint that all must adopt. This idea pries apart two notions that had often been blended together. On one hand, there might be a common spatial stage in which events happen, a shared geometry that different observers can describe. On the other hand, the question of who is really moving or really still becomes less meaningful. If every inertial observer, that is, every observer, moving at a constant speed in a straight line, can treat themselves as being at rest for the purposes of their own measurements, then the state of absolute rest begins to fade from physics. What matters instead is the relative motion between one frame and another. We can let that distinction simply rest in the background. Now we picture Galileo's cabin not just as part of a ship, but as part of a much larger set of motions. The vessel sits on Earth's surface, and Earth itself spins around its axis in a daily rotation. That rotating planet travels around the Sun, tracing a nearly elliptical path at tens of thousands of kilometers per hour. The Sun, in turn, orbits the center of the Milky Way, carried along with its retinue of planets and comets. The galaxy itself moves relative to neighboring galaxies, drawn by the combined gravity of clusters and filaments spread across space. Each layer adds a new velocity, a new direction, a new sense in which the cabin is in motion. Yet the person inside the windowless room has no awareness of this layered movement. The floor feels stable underfoot. A ball tossed gently from hand to hand follows a simple arc. The air does not rush past as it would near an open hatch. If all of these motions are steady and unchanging, they do not disturb the local experiments being carried out. In practice, we spend our entire lives in situations like this, carried through space by planetary, stellar, and galactic journeys that we do not directly sense. The feeling of being still is often just the experience of sharing the same steady motion as our surroundings. In this way, Galileo's picture of the ship becomes a small model of the universe. Every observer, whether on a vessel at sea on a planet or near a star can adopt their own frame and treat themselves as stationary for the purposes of describing local physics. Velocities are then described relative to that chosen frame. The shore recedes, the sky appears to rotate, the stars seem to drift over long periods. No experiment strictly confined to the cabin picks out a single, absolute definition of rest. Instead, physics must be built so that its basic laws take the same form in all such inertial frames. This perspective sets the stage for later developments. Newton would go on to formulate laws of motion and gravity, using space and time as a fixed backdrop, while still respecting Galileo's relativity of uniform motion. Leibniz would argue more strongly that space is nothing over and above the relations between objects. Much later, Einstein would reshape both space and time into a single spacetime, in which the speed of light is constant for all observers, and gravity becomes a manifestation of curvature rather than a force acting at a distance. The seeds of that long evolution lie in the simple realization that being at rest is not an absolute condition, but a matter of reference. For our purposes, it is enough to remain with the image of the closed cabin, nested inside layers of motion, all moving through a wider cosmos. The plates on the table, the fish in the tank, the small flying creatures in the air, and the person standing on the floor share the same broad journey. And so, to them, their immediate surroundings feel steady. Out beyond the walls, planets rotate, stars orbit, and galaxies turn. And yet the local behavior of falling objects and moving bodies can be described without ever needing to know that vast external dance. Somewhere between the ancient idea of space as a cradle and the later picture of relative motion, a quieter understanding of where and how fast begins to emerge, ready to be woven into deeper questions about what space and time themselves might be. After the work of Galileo, long after the first telescopes had tilted upward toward the sky, questions about space did not fade. They settled into the minds of two remarkable thinkers, Isaac Newton and Gottfried Wilhelm Leibniz, who found themselves circling the same issue from very different directions. Whether space exists as something in its own right, or whether it is only a way of talking about the distances and relations between things. We can picture the world in the middle of the 17th century, with maps of continents still being redrawn, with new instruments slowly improving, and with old philosophical systems beginning to loosen. Newton, born in England in 1642, grew up in a landscape of fields, universities, and observatories that would eventually nourish his precise, mechanical picture of nature. Leibniz, born a few years later in a region that is now Germany, moved among libraries, courts, and academies, drawn to questions about logic, language, and the reasons anything exists at all. Their lives never converged in a shared room, yet their ideas met and tangled across letters, manuscripts, and reports that traveled through the scientific networks of Europe. Both of them developed the mathematical tools we now call calculus, ways of tracking how quantities change and accumulate. The question of who arrived first became a source of tension and pride. And the priority dispute left marks on their reputations and their impressions of each other. Beneath that surface quarrel, though, lay a deeper difference. Newton's instincts leaned toward forces, masses, and trajectories, like an immense clockwork in which objects obeyed simple rules. Leibniz's instincts turned toward patterns of connection and meaning, asking why there is something rather than nothing, and how the structure of the world might reflect an underlying order of relations. The names can blur into the background. What matters for us is the shape of the disagreement. For Newton, the universe needed a kind of stage on which all motions could be measured. To explain this, he invited his readers into a thought experiment that has become famous: the rotating bucket. We imagine a bucket of water hanging by a rope. At first, everything is still, and the surface of the water lies flat and level. Then the bucket is twisted and released. The bucket begins to spin, but the water lags behind, and for a moment the surface remains nearly flat while the wooden sides blur around it. As the bucket keeps turning, friction drags the water into motion, and slowly the surface curves upward at the edges, forming a shallow hollow in the center. Newton asked what this curve is telling us. If motion were only about how one object moves relative to another, then the crucial comparison would be between the water and the bucket. At the very beginning, when the bucket swings into motion but the water still rests, their relative motion is large, yet the surface remains flat. Later, when both bucket and water spin together and their relative motion is small, the surface is curved. This mismatch suggests that the shape of the water cannot be explained only by comparing it to the bucket. For Newton, the simplest conclusion was that the water is rotating with respect to something else, something more fundamental than any nearby object. From this line of thought, he was led to the idea of absolute space, a background that exists whether or not it contains matter. In his description, absolute space is uniform and unmoving, always the same, not influenced by the events that take place within it. Time, in his view, shares this independence. Absolute time flows at a constant rate, unaffected by the motions or changes of objects. The world of planets, comets, falling apples, and spinning buckets plays out like a performance on an enormous, invisible stage that never shifts and never speeds up or slows down. Once this stage is assumed, the laws of motion and universal gravitation can be written as clear equations that relate forces, masses, and accelerations measured against this fixed background. For our purposes, we can simply hold the image of a vast, rigid arena in which all positions and times can be labeled without ambiguity. Leibniz looked at the same universe and found this picture unsatisfying. He did not accept the idea of an empty space that would still somehow exist even if every particle of matter were removed. For him, what is real are the objects and the relations among them. Distances, directions, and intervals between events. Space, in that relational sense, is a way of talking about how things are arranged with respect to one another. Time is a way of talking about the order in which events occur. If we imagine, as a thought experiment, that all matter, radiation, and fields are removed from a region, he would say that there is nothing left to measure, no distances to define, no events to order. And so the talk of remaining space without content loses its grounding. In this view, saying that the universe could be shifted 5 meters to the east with no observable difference makes no sense, because such a shift would not change any relation among its parts. The only meaningful statements are about how objects stand in relation to each other. If every planet, star, and atom keeps exactly the same pattern of separations and motions, then there is no further fact about their absolute position in a larger container. Where Newton trusted the notion of absolute coordinates, Leibniz trusted the network of relations. This way of thinking about space and time as relational would, much later, resonate with how some physicists interpret space-time in Einstein's theories as something molded by matter and energy, rather than a rigid box that exists independently. But in the era of Newton and Leibniz, it remained largely a philosophical stance, discussed in letters and essays rather than tested in observatories. It suggested that the universe does not sit inside a pre-existing frame. Instead, the frame is woven out of the pattern of contents. While they argued in their writings, the practical successes of Newton's mechanics carried enormous weight. His laws of motion and his law of gravitation allowed astronomers to calculate planetary orbits with new accuracy, to predict eclipses, and to understand the paths of comets that appeared, vanished into the outer dark, and then returned. The ability to describe these phenomena with a single, coherent framework led many to accept not only the equations, but also the underlying picture of absolute space and absolute time as the correct foundation for physics. For nearly 2 centuries, this framework guided the way scientists thought about motion. Within it, the relative motions described earlier by Galileo still mattered. A ship's cabin, a moving train, a planet gliding along its orbit all provided local frames in which the laws took the same form. Yet behind all these shifting perspectives, there was assumed to be a deeper, unmoving reference, the absolute space and time that Newton had described. The distinctions among rest and motion, acceleration and rotation, were ultimately defined with respect to that silent background. We can let that stage linger in our minds, an immense, uniform arena, existing whether or not anything happens inside it. From our present vantage point, we know that this picture will not remain the final word. Relativity will show that time does not tick at the same rate for all observers, that space and time can mix and curve, and that no single frame stands above all others. The success of Newton's system, however, reminds us that a theory can work extraordinarily well for a wide range of situations and still be incomplete at a deeper level. The orbits of planets, the fall of stones, the swing of pendulums, and even the rotating bucket can all be described with high precision, while the underlying notions of an absolute stage begin, quietly, to loosen. For now, we stay with the image of these two thinkers, separated by geography and temperament, yet joined by a shared attempt to understand the setting in which events unfold. One of them trusts a fixed arena that exists whether or not it is occupied. The other trusts only the web of relations among the actors on that arena. Between them, a question remains suspended: whether space and time are entities in their own right, or patterns emerging from the placement and succession of things. As we drift forward toward later ideas, that question will follow us, changing shape as the architecture of space and time is rebuilt in new terms. From the mechanical stage of Newton, with its forces and orbits and steady trajectories, our attention slides toward a different landscape, one made of coal fires, pipes of hot metal, and clouds of steam, where time is no longer just a coordinate in an equation, but begins to show a distinct direction in the way processes unfold. We find ourselves in the 19th century, in workshops and mines where people ask simple, practical questions. How much coal does it take to do the work of a horse? How long can a machine run before it needs fuel again? And how efficiently can heat be turned into motion? In a steam engine, coal is burned in a furnace, heating water in a boiler until the water turns into pressurized vapor. That vapor pushes on pistons, drives wheels, lifts loads. Yet not all of the energy from the burning coal reaches the wheels. Some of it escapes as hot exhaust, some of it warms the boiler walls, some of it is lost to friction between moving metal parts, heard as rattles and hisses and felt as warmth on nearby surfaces. Engineers discover, as they measure and adjust, that no matter how they improve their designs, some portion of the input energy always slides away into forms that cannot be fully recovered for useful work. We can picture rows of engines in a factory, each one drawing in fuel, boiling water, moving pistons, and constantly spilling some of its ordered energy into the wider environment. The desire to quantify this spill, to understand the theoretical ceiling of efficiency, leads scientists to formulate the principles of thermodynamics. At first, these principles look like rules about machines. Limits on how much work can be extracted from a temperature difference, relationships between heat flow and mechanical output. Yet as the thinking deepens, it becomes clear that these are not just engineering guidelines. They hint at a broader pattern that applies to every physical process, from boiling water to the behavior of gases in the atmosphere, and eventually to the evolution of the cosmos. In this new language, entropy appears as a measure that tracks how energy is spread among the possible microstates of a system. One way to make this less abstract is to imagine a gas in a container, made of countless invisible molecules bouncing in all directions. A configuration in which all the molecules happen to be crowded into one corner of the container is possible, but extremely unlikely. A configuration in which the molecules are distributed more evenly is overwhelmingly more probable. George Gamow and others use images like air in a room spontaneously gathering into a small region. Not absolutely forbidden by the equations, but so improbable that, even if we waited far longer than the current age of the universe, we would not expect to see it happen by chance. When we mix hot and cold fluids together, they blend into a uniform medium with intermediate temperature. The mixed state corresponds to many more microscopic arrangements than the neatly separated state. The second law of thermodynamics expresses, in formal terms, a pattern that we recognize from daily life. Left to themselves, Isolated systems tend to move toward configurations that are more probable, which typically means more uniform and less structured. Entropy in an isolated system does not spontaneously decrease. It either stays the same or increases. This preference introduces a built-in direction. We remember ice cubes melting into water much more easily than we can picture a glass of water, left alone, assembling ice cubes. We do not need to count molecules for this direction to be felt. Some thinkers of the 19th century take this local pattern and stretch it out to cosmic scales. William Thomson, better known as Lord Kelvin, reasons that if every process in nature takes energy in forms that can do work and eventually spreads that energy into more uniform heat, then, over sufficiently long spans, the entire universe should drift toward a state where temperature differences are ironed out. In such a state, there would be no gradients to drive engines, no flowing rivers of energy to build or sustain complex structures. His phrase, "a universal state of rest and lifelessness," gives a stark portrait. A cosmos that has reached thermodynamic equilibrium, in which nothing much happens because there is no usable free energy left to fuel change. We can imagine this not as a sudden event, but as a slowly emerging condition. Early in cosmic history, when the universe was filled with hot plasma and steep temperature contrasts, entropy was lower. There were many ways in which energy and matter could rearrange themselves as expansion continued. As stars formed, shone, and burned through their fuel, they increased entropy by radiating energy into the cooler surroundings. As structures collapsed under gravity and then radiated away energy, they did the same. Over time, the sum of these processes leads toward a situation where further large-scale rearrangements become rare. The concept of heat death is, in this sense, a thermodynamic extrapolation. If entropy keeps increasing and there is a maximum possible value compatible with the total energy and volume, the system moves toward that maximum. Into this picture, James Clerk Maxwell introduces a famous thought experiment that seems at first to challenge the second law. He asks us to imagine a tiny being, often called a demon, who stands at a small door between two chambers of gas. This being can see the individual molecules and distinguish their speeds. Whenever a fast molecule approaches from one side, the demon opens the door to let it pass into one chamber. Whenever a slow molecule approaches from the other side, the demon opens the door in the opposite direction. With quick responses and careful choices, the demon could accumulate faster molecules in one chamber and slower ones in the other, seemingly separating hot from cold without expending any work, and thereby decreasing entropy in defiance of the usual trend. We may picture the demon as an almost weightless attendant at a border checkpoint, constantly flipping a tiny gate in response to molecular arrivals. The image raises a deep question. If information can be used in this way to manipulate the distribution of energy, what role does information play in the accounting of entropy? For many years, the paradox remains a fertile source of discussion. It seems that, by using knowledge about individual particles, the demon has found a way to create a more ordered state from a less ordered one, without paying the usual thermodynamic cost. Later analysis, particularly through the work of Rolf Landauer and others, reframes the problem by focusing on the demon's memory. To sort molecules, the demon has to store and process bits of information. Records of which molecule went where, decisions about which way to open the door. At some stage, to continue operating, the demon must erase or overwrite parts of this memory. Landauer shows that the erasure of one bit of information in a physical device has an unavoidable minimal energy cost, which appears as heat dissipated into the environment. This principle connects logical irreversibility, the loss of information in operations like resetting a register, to thermodynamic irreversibility. In a modern computer chip, logical gates route electrical signals, and whenever two different inputs are forced into the same output state in a way that forgets which path was taken, information is erased. The device warms slightly as it operates, and that heating is one manifestation of the underlying thermodynamic cost that Landauer's limit describes. Experiments with carefully designed microscopic systems have measured heat dissipation during single-bit erasure and found results consistent with the theoretical prediction. In this way, the abstract symbol of a bit becomes tied to real exchanges of energy and entropy. This connection suggests that the arrow of time we noticed in steam engines also appears in any system that processes information. Every time a computation discards intermediate data, every time a memory device overwrites old content, entropy increases in the combined system of device plus environment. The direction from past to future can be associated with the accumulation of such losses. Once information has been irreversibly dispersed into microscopic degrees of freedom, recovering it would require unlikely fluctuations similar to the improbable clumping of gas into one corner of a room. Time, in this view, is intertwined with what can be remembered and what has been irretrievably blurred. We can hold an image of many different arrows merging, heat flowing from warm regions to cooler ones, ordered structures slowly breaking down, computation generating waste heat as it discards bits, and, on the largest scales, the cosmos stepping from low entropy beginnings through stages of increasing disorder. All of these arrows point in the same temporal direction. The fact that we recall the past and anticipate the future rather than the other way around matches this alignment. Records exist because physical processes have left stable traces in one direction of time, not the reverse. At this point, a further question quietly appears. If we imagine a universe that has reached a state in which entropy is essentially maximal, in which temperature gradients are negligible and no large-scale structures are changing, what would it mean to say that time is passing? In such an environment, an observer, if any kind of organized system could still persist, would see almost no difference between one moment and the next. Without observable change or accessible records of transitions, the distinction between before and after becomes harder to define. Time, which in earlier eras could be associated with the progression of states and the fading of order, might continue as a parameter in equations but lose some of its experiential content. We do not need to push this scenario to its limit. It is enough to notice how closely our sense of temporal direction is tied to gradients, to flows, to the steady increase of entropy and the accompanying loss of detailed information. When gradients vanish and processes slow to a near standstill, the arrow of time becomes faint. Somewhere far away in this same universe, we might remember the thin shell built around a black hole, with its inhabitants using the remaining free energy and the curvature of space-time to stretch their history across more of cosmic time. Their existence depends on the very gradients that the second law predicts will eventually smooth out. As entropy continues to grow and the background cools further, even their elaborate engineering would face the same thermodynamic limits. The story that began with coal and steam, with engines churning in 19th century workshops, thus reaches out to the largest scales, linking the efficiency of machines, the randomness of molecular motion, the cost of erasing a bit, and the long-term evolution of the cosmos. From here, it is natural for our attention to drift toward another transformation, one in which space and time themselves are no longer fixed backgrounds but dynamic participants, curving and stretching in response to matter and energy, and offering yet another way of thinking about how events are arranged in the universe. After spending time with engines, entropy, and the one-way drift of thermodynamic processes, our attention moves back out into the dark, towards something that seems almost weightless, light, crossing space at its own fixed pace and quietly reshaping how we think about distance, motion, and time itself. Long before lasers, satellites, or precise clocks in laboratories, astronomers watched the moons of Jupiter slip into and out of shadow. Ole Roma noticed that one of those moons, Io, did not keep to a perfectly regular schedule when seen from Earth. Sometimes its disappearances behind Jupiter came a little earlier than expected, sometimes a little later. As Earth moved around the Sun, there were times when we were closer to Jupiter and times when we were farther away. When the distance was greater, the light from Io needed extra time to reach us, and the predicted eclipses appeared delayed. When the distance shrank, the light had a shorter path, and the events arrived ahead of schedule. By treating these shifts as the ticks of a natural clock and comparing them with Earth's changing position, Roma and others could infer that light does not move infinitely fast. It has a finite speed that can be estimated from these celestial delays. More careful reasoning by Christian Huygens gave a value that was high but still finite, a specific number that could sit in equations and be measured again in other ways. Once light is understood to have a definite speed, a new question emerges almost immediately. What kind of thing is moving at this speed, and what is it moving through? In the 19th century, James Clerk Maxwell combines electricity and magnetism into a single framework, writing down equations that describe how changing electric fields create magnetic fields, and how changing magnetic fields create electric fields. When these equations are examined, they predict waves that travel through empty space with a speed that matches the measured speed of light. The natural conclusion is that light itself is an electromagnetic wave, a self-sustaining pattern of electric and magnetic fields that travels without needing any obvious material medium. Yet, the idea of a wave without a medium is hard to accept at first. Waves on water need water. Waves of sound need air or another substance to carry compressions and rarefactions. Many physicists assume that there must be some subtle, invisible medium filling the universe, an ether that supports electromagnetic waves the way air supports sound. If light is a wave in this ether, then its speed should be measured relative to that medium. And Earth, as it travels around the sun, should move through the ether with some velocity. That motion ought to show up as small differences in the measured speed of light in different directions, like feeling a breeze differently when walking into the wind or with it. Careful experiments are built to look for this effect. In one famous arrangement, beams of light are split, sent along perpendicular paths, reflected, and recombined, in the hope that motion through the ether will cause detectable shifts in the interference pattern. Again and again, measurements come back with no significant difference. No matter how Earth moves in its orbit, no reliable signature of an ether wind appears. The speed of light seems to be the same in all directions to within the sensitivity of the instruments. The situation becomes awkward. Maxwell's equations predict a specific speed. Experiments confirm that speed, but attempts to identify a preferred rest frame for the ether keep failing. At this crossroads, Albert Einstein takes a different approach. Instead of adding new mechanisms or tweaking Maxwell's equations, he starts from two postulates. First, the laws of physics take the same form in all frames that move at constant velocity relative to one another. Second, the speed of light in vacuum has the same value in all such frames, regardless of the motion of the source or the observer. These statements are simple to say, but they carry deep consequences. We can return, in thought, to Galileo's ship, now updated. Inside a smoothly moving vessel with no jolts or swaying, experiments behave as they would on shore. Balls tossed upward land back in the thrower's hand. Sparks fall straight down to the deck. In Einstein's view, this equivalence extends to light beams and measuring devices. Whether our laboratory is at rest on Earth or gliding through space at steady speed, when we send a pulse of light from one mirror to another and back, we measure the same value for its speed. A distant observer watching the same experiment from another inertial frame also finds the same speed, even though, from that perspective, the entire laboratory is in motion. For both measurements to be correct, space and time can no longer behave as in Newton's picture. Lengths along the direction of motion and intervals of time between events must adjust in such a way that the combined description leaves the speed of light unchanged. Observers in relative motion will disagree about the lengths of moving objects, about how fast clocks tick, and about whether two distant events are simultaneous. There is no single universal time that all observers share. Instead, each inertial frame comes with its own slicing of space-time into space and time, and these slicings tilt relative to one another depending on the state of motion. Hermann Minkowski, who once taught Einstein, takes these ideas and gives them a geometric form. Rather than treating space and time separately, he proposes that we think in terms of a four-dimensional space-time, with three spatial dimensions and one temporal dimension combined into a single structure. Each event, a flash of light, a collision of particles, a reading on a clock at a specific place, is a point in this four-dimensional continuum. The history of an object is a world line, a curve that threads through space-time, representing where and when the object exists. In this picture, switching from one inertial frame to another is like performing a kind of rotation and stretching in space-time, rearranging how we slice the four-dimensional whole into space at an instant and time between slices. The invariant quantity is not a separate distance or duration, but a combined space-time interval which all observers agree on, even as they disagree about its decomposition into space and time components. Light follows special paths in this geometry, moving along null directions that mark the ultimate speed at which influences can propagate. A flash of light emitted at one event traces out a cone of possible arrival events. Anything inside that cone can be causally affected by the emission. Anything outside cannot. We can let this geometric stage settle gently in the mind as a backdrop. Einstein then extends the relativity principle beyond uniform motion to include accelerating frames and gravitational effects. In the theory of general relativity, published in 1915, gravity is no longer treated as a force that acts at a distance between masses, as in Newton's formulation. Instead, mass and energy tell spacetime how to curve, and curved spacetime tells matter and light how to move. Free-falling objects follow geodesics, which are the straightest possible paths in a curved geometry, even though, when projected into space, those paths may look like arcs or spirals. Near a massive body, such as a planet, star, or black hole, spacetime is more strongly curved. Light rays that pass near such an object do not travel in perfect straight lines in space. They bend so that distant stars can appear slightly displaced from their true positions when their light grazes a massive body on its way to us. Time is affected as well. A clock on the surface of Earth, deeper in the gravitational field, ticks a bit more slowly than a similar clock higher up, where the gravitational potential is slightly different. This difference is small on everyday scales, but measurable with precise instruments. Near very compact masses, like neutron stars or black holes, the effect becomes dramatic. In the vicinity of a black hole, space-time is curved so intensely that the paths of light and matter lead inward toward the event horizon, a boundary beyond which signals cannot reach distant observers. For someone hovering safely at a distance, watching a clock that is closer to the black hole, the closer clock appears to slow. Processes near the horizon seem to take longer and longer, stretched by gravitational time dilation. From the viewpoint of an observer who stays near the black hole, their own time feels normal. It is the distant universe whose clocks appear to run differently. Time passes at different rates depending on both motion and gravitational environment. And there is no single cosmic clock that all observers can share. The structure that Minkowski described becomes dynamic in this setting. Space-time is no longer a rigid arena, but a responsive fabric that can curve, ripple, and evolve. Massive bodies create wells and hills in this fabric. Orbiting objects are like marbles, rolling along geodesics in these contours. When massive bodies such as black holes or neutron stars orbit each other and merge, the changing gravitational field sends out waves, small disturbances in the curvature that travel outward at the speed of light. These gravitational waves stretch and squeeze distances very slightly as they pass, altering the separation between freely suspended mirrors or test masses by amounts far smaller than the size of an atom. On Earth, instruments like LIGO and Virgo use long arms with laser beams reflected between mirrors to look for these passing waves. When a gravitational wave moves through the apparatus, one arm may become slightly longer, while the other becomes slightly shorter. And this difference shows up as a shifting interference pattern in the recombined light. The signals that have been detected correspond to events billions of light years away, where pairs of compact objects spiraled together and their final orbits stirred space-time strongly enough to send out measurable ripples. In this way, the idea of space-time as an active medium becomes more than a mathematical image. It appears directly in the data recorded by our detectors. Experiments with clocks also confirm the relativistic picture. In one series of flights, precise atomic clocks are carried around the world on commercial aircraft. then compared to similar clocks that stayed in laboratories. The traveling clocks experience both higher speeds and slightly different gravitational potentials. And their readings, when brought together, diverge by amounts that match the predictions of special and general relativity combined. Even everyday technologies, such as satellite navigation systems, must account for both types of time dilation. The onboard clocks tick differently from clocks on the ground because satellites move quickly and reside in weaker gravity. And without correcting for these relativistic effects, the positioning data would drift. We can imagine all of this woven into the larger cosmos, an expanding space-time in which distant galaxies recede as the metric itself grows. Light from early clouds of plasma stretching into the deep infrared glow of the cosmic microwave background, and regions where mass curves the fabric strongly enough to form black holes that slow time near their horizons. The speed of light acts as a constant thread through this tapestry, a maximum signal speed that shapes what can influence what and when. Gravity is not a force binding objects across empty space, but a reflection of the geometry in which their world lines unfold. Some exact solutions of Einstein's equations even allow for closed loops in space-time, paths that return to their own past. Although whether such configurations can exist in a realistic universe is still a matter of careful analysis rather than paradox stories. What matters for our drift through this landscape is the sense that space and time have fused into a single, elastic structure, one that can stretch with cosmic expansion, curve around masses, carry waves, and provide a setting where different observers carve out their own measures of distance and duration. Somewhere out in that structure, a lonely black hole may still be surrounded by a thin, artificial shell, with a civilization using gravitational time dilation to extend its story against the slow backdrop of entropy and expansion. Their clocks, deep in a well of curved space-time, mark a local rhythm that does not match the rhythm of distant galaxies. Yet both are threaded through the same four-dimensional continuum. As we stay with this image, the rigid absolute stage of Newton gives way to a space-time that moves and bends, and the constant speed of light becomes the line along which our understanding of space and time has been quietly rewritten. When Einstein turned his equations from local systems toward the entire cosmos, the geometric stage we have been tracing did something unexpected. It did not merely curve around isolated masses. On the largest scales it could stretch, changing its overall size as time went by. And that shift began to raise oddly simple questions about energy and about what we mean by space in the first place. In the early 20th century, Alexander Friedmann looked at Einstein's field equations and asked what they would say about a universe that is, on average, the same in every direction and at every location, at least when we look on very large scales. Instead of assuming a static cosmos, frozen in place, he allowed the scale factor, the overall size of space in the model, to change over time. The equations then permitted solutions in which that scale factor grows or shrinks. Not long after, Edwin Hubble measured the light from distant galaxies and found that their spectral lines were shifted toward the red end of the spectrum. The farther away a galaxy was, the more its lines were shifted, and the inferred recession speed increased roughly with distance. This relation could be expressed as so many kilometers per second for every megaparsec of separation. We can picture a grid drawn through space, with galaxies loosely carried along on its nodes. As the grid stretches, the distance between far-flung nodes increases, and light that crosses this expanding pattern has its wavelength stretched as well. The redshift is not just a Doppler effect from galaxies flying through fixed space like sparks from a firework. It is a record of space itself, having grown while the light was on its way. In this view, the history of the universe is not a series of events inside a rigid container, but the evolution of the container's own scale. Tracing the expansion backward suggests a time when matter and radiation were compressed into a much hotter, denser state, which we now call the early universe, leading into what we summarize as the Big Bang picture. The expansion is not felt uniformly in every corner of reality. On the scale of a galaxy, gravity binds stars together into a rotating disk and halo. On smaller scales, electromagnetic forces hold atoms and molecules. and more complex interactions hold planets and living bodies together. These bound structures are not stretched along with the expansion, the way the distance between remote clusters is. A convenient image is a flexible sheet being gently pulled from its edges, while heavy objects placed on it make dimples. Where the dimples are shallow, points on the sheet drift farther apart as it is pulled. Where the dimples are deep, material has fallen in and is held together by gravitational attraction, resisting the overall stretching. Our own solar system sits inside one of those deep dimples. The distance between Earth and the Sun does not grow because the local gravitational potential dominates over the very small cosmological effect on that scale. The same is true, in a different way, for the atoms in our bodies, where the forces between charges are far stronger than any influence from cosmic expansion. Only on scales much larger than galaxies does the stretching of space become the main effect, turning the arrangement of distant clusters into a kind of moving pattern in which everything slowly separates. We can leave that contrast between bound regions and expanding distances as a background image. As cosmologists became more comfortable with this dynamic space-time, they also began to examine what it meant for some of the deep principles taken almost for granted in earlier physics, such as conservation of energy. Emmy Noether discovered a powerful connection between symmetries and conserved quantities. If the laws of physics are invariant under shifts in time, if they look the same today as they will tomorrow, then there is a conserved quantity we identify as energy. If the laws are invariant under shifts in space, if they look the same here and there, then momentum is conserved. Her theorem makes these associations precise. In a static space-time like the one Newton imagined, or even in special relativity with no cosmic evolution, it is natural to say that the total energy of an isolated system is conserved, provided the underlying symmetries are in place. In an expanding universe, however, the situation is subtler. The geometry of space-time itself changes as the scale factor grows. The metric that tells us how to measure distances and times is not invariant under a simple shift forward in cosmic time. Yesterday's universe is not exactly the same as today's. There was literally less space then, in the sense of a smaller scale factor. On these global scales, the symmetry in time that underwrites a clear, conserved total energy becomes ambiguous. A familiar example appears in the behavior of photons traveling through this expanding cosmos. As space stretches, the wavelength of each photon is stretched with it, and its energy, which is inversely related to wavelength, decreases. A photon emitted in the visible range in the early universe may arrive today as a microwave photon with far lower energy. For a single photon, we can calculate how much energy has been lost. For a whole bath of radiation, such as the cosmic microwave background, we can track how its energy density drops as the universe expands. The question then arises, if energy is conserved, where did that energy go? In a small static system, we would expect to find it transferred into some other form. But in the cosmological setting, there is no simple ledger in which the missing energy appears as another term. One way to say this, consistent with Noether's insight, is that the notion of a globally conserved energy for the whole universe does not have the same clear status in a space-time that changes in time and lacks the right symmetry. Local conservation, expressed in the way energy and momentum flow in and out of small regions, still holds through the field equations. But the idea of adding up all contributions over the entire universe and insisting on a single, invariant total becomes less meaningful when the very geometry is evolving. This is one of the places where our everyday intuitions, shaped by closed systems and isolated experiments, rub against the broader structure of general relativity in cosmology. It can feel as if a principle that once seemed almost sacred has been softened, not by violating it, but by revealing that its cleanest form belongs to a more limited setting than we first assumed. Against this backdrop, some physicists have chosen to speak about space-time in surprisingly austere terms. Steven Weinberg, reflecting on the role of space-time in relativity, suggested that, in a precise sense, space-time is not a substance with its own independent properties, but a way of organizing the behavior of fields and particles. The curved manifold, with its metric and connections, can be seen as a mathematical construction that efficiently encodes the relationships among events, rather than as a tangible fabric with its own material nature. The image of a rubber sheet stretching and bending is useful for intuition, but the deeper reality may be closer to a web of relations described by equations than to a medium that can be pulled and torn. This perspective loops us back to the old conversation between Newton and Leibniz. General relativity made space-time feel more physical by allowing it to curve, ripple, and guide motion. Yet at the same time, in views like Weinberg's, it also invites us to treat that curved structure as a sophisticated bookkeeping device for interactions. In that sense, the background on which events unfold and the events themselves are tied together more tightly than either realist or relational pictures from earlier centuries might have suggested. We can let this tension remain unresolved, hovering between images of an expanding fabric and a network of correlation. Somewhere in the far future of this expanding universe, we might return to the imagined civilization that built its shell around a solitary black hole. They lived deep in a well of curved space-time, using gravitational time dilation to stretch their own history across a longer span of cosmic evolution. Their engineers are fluent in the practical side of relativity. They can calculate orbits in strong fields, design structures that balance tidal forces, and harvest what remains of free energy in a cosmos edging toward equilibrium. For them, space-time is a tool, a way of predicting trajectories, adjusting clocks, and planning how to extract the most life from the conditions they inhabit. Yet, even they might not know what space-time ultimately is. They may speak about curvature and horizons, about expansion and redshift, just as we do. They may rely on precise models to steer their habitats and guide their instruments. But the question of whether the geometry they manipulate is a fundamental entity or a description emerging from something deeper could remain as open for them as it is for us. Their situation highlights a gap between technological mastery and foundational understanding. We already see this in our own era, where relativity is part of the design of global positioning systems and the interpretation of gravitational wave data. While the most basic questions about quantum fields, information, and the origin of space-time continue to invite new ideas. Around their black hole, the thin shell holds its shape against expansion, anchored by gravity even as distant galaxies slide away on the stretching grid of the universe. Photons from those galaxies reach the shell with longer wavelengths than when they set out, carrying the imprint of expansion in their tired colors. The inhabitants can measure the change, trace the history of the scale factor, and watch as ever more of the cosmos drifts beyond their horizon. The dynamic space-time that made their refuge possible is also the medium through which their wider surroundings gradually recede. In this scene, the expanding universe, the ambiguity of global energy, and the relational nature of space-time all come together. Space seems to grow, yet may not be a thing that grows. Energy seems to leak from photons as they redshift, yet may not be lost in any conventional sense. Space-time seems to be both stage and script, both medium and pattern. As we stay with these overlapping views, a new set of questions begins to form about whether space and time themselves might arise from something more basic, perhaps related to quantum information or deeper symmetries, and how such an emergence would fit into the long story traced from early plasma to far future black holes. When we look at the universe through the lens of space-time, there is a particular picture that begins to emerge, slow and steady, as if all events are arranged inside a single four-dimensional sculpture. In that picture, called the block universe, past, present, and future do not truly flow past some special moment called now. Instead, every event sits at its own coordinates, and what we experience as the passage of time is a way of moving through this block along one thin path. In this view, every particle has a world line, a thread in space-time that shows where and when it exists. The atoms in our bones, the molecules in the air, the photons crossing the room, each can be imagined as tracing their own continuous lines from one event to the next. What we call a person is a bundle of countless such world lines braided together for a finite stretch, intertwining for a while before separating again as matter is recycled, as particles drift away or are incorporated into other structures. Birth is the beginning of a particular pattern in this bundle. Death is a change in the way the lines group. But the entire pattern has a place in the four-dimensional whole. From far outside this picture, if we could adopt a purely geometric point of view, there is no unique surface that deserves to be called the present. Different observers, moving at different velocities, slice space-time into nows in different ways. The relativity of simultaneity means that what counts as at the same time in one frame does not match what counts as at the same time in another. The block contains all events, from the earliest moments of the universe to the far future. And our local sense of now is just one particular slice, depending on how we are moving and where we are. It can feel as if this picture is telling us that everything is already laid out, that every choice and outcome has its place in the block. Yet the equations that describe the world lines do not carry emotional weight themselves. They simply describe relations between events. Our sense of moving from an open future into a settled past is part of the pattern too, associated with memory, with records, and with the direction in which certain physical quantities change. If we step down from this global view and look at the basic laws that govern small systems, we find something striking. Many of them do not care whether time is running forward or backward. The equations that describe how two electrons repel each other or how molecules scatter in a gas are almost symmetric under time reversal. If we filmed a few particles bouncing off one another and then played the film backwards, the reversed motion would still obey the same microscopic laws. The trajectories would look entirely plausible, each collision conserving energy and momentum just as neatly as in the forward version. By contrast, when we watch a glass falling and shattering, or smoke dispersing into a room, playing the film backwards looks immediately wrong. Fragments do not spontaneously leap together to form a whole glass. Smoke does not gather itself neatly back into a compact swirl. On the scale of everyday experience, processes have a direction that is easy to recognize. Things mix, crumble, spread, and wear out. Fires burn fuel and do not, on their own, unburn themselves. The difference between these two levels, microscopic reversibility and macroscopic direction, is where entropy re-enters the story. On the level of many particles, what matters is not just what is possible in principle, but what is overwhelmingly likely given the number of ways the system can be arranged. Low entropy states, with matter arranged in special, ordered patterns, occupy a tiny region in the space of possibilities. High entropy states, more spread out and disordered, occupy a much larger region. If a system starts in a low entropy state, typical evolution under time-symmetric laws will carry it into the vastly larger set of high entropy configurations. The behavior we see, eggs breaking rather than unbreaking, is a reflection of this statistical tendency, not of any built-in preference in the microscopic equations themselves. So if the fundamental rules almost do not care which way time runs, why does our universe display such a consistent arrow from earlier low entropy to later high entropy? The answer appears to lie in the conditions at the beginning. When we look back, using observations of the cosmic microwave background and models of early cosmology, we find that the young universe was hot and dense, but also remarkably smooth. Matter and radiation were spread out, with only tiny fluctuations. The primordial plasma was nearly uniform, with small ripples in density that would later grow into galaxies and clusters under the influence of gravity. This smoothness is, in an important sense, a highly ordered state. For ordinary gases, a smooth distribution is often associated with high entropy. For gravity, the situation is different. A uniform cloud of self-gravitating matter has many ways to rearrange itself into more complex structures. Stars, galaxies, black holes. In that sense, the early smooth universe had a great deal of room for gravitational entropy to increase. As time goes on, matter clumps, structures form, radiation is emitted, and the overall gravitational configuration moves into more typical, more disordered states. The low entropy character of the early cosmos is not about temperature alone, it is about how matter was arranged in the gravitational field. We can imagine that first plasma as a fine mist, almost the same everywhere, with just enough irregularity to allow gravity to start gathering material into denser regions. If it had started out already filled with collapsed objects and chaotic structures, the freedom for entropy to grow further would have been limited. In that alternate scenario, the arrow of time, at least in the thermodynamic sense we recognize, might be very different, or hardly present at all. Roger Penrose has tried to quantify how unusual the actual initial state appears to be. His estimates suggest that the probability of a universe beginning in such a low-entropy gravitational configuration, if all microstates were equally likely, would be extraordinarily small. Writing the number explicitly would require more zeros in the denominator than we can comfortably picture. 1 divided by 10 raised to a power that is itself a number with over 100 digits. The exact details are less important here than the impression that this starting condition is highly special in the space of possibilities. From this perspective, the arrow of time we experience could be seen as a consequence of that special beginning. The laws themselves, whether classical or quantum, are mostly symmetric under reversing time. What breaks the symmetry in practice is the fact that the universe began in a particular kind of state and not another. Given that beginning, typical evolution leads from low entropy to higher entropy. The one-way character of macroscopic processes, the difference between memory and anticipation, the distinction between what we call before and after, all trace back to that boundary condition. A metaphor that sometimes helps is the mixing of paints. Suppose we start with a container in which layers of different colors are neatly arranged. Stirring them leads to a uniform mixture. The microscopic rules for how molecules move do not favor one direction in time. They would allow, in principle, a film where the mixture unstirs and reforms layers. But given the initial condition of stratified paint, the typical evolution is toward mixing, and we point to that direction and call it forward. We label the layered state as past and the mixed state as future. The arrow does not come from the equations alone. It comes from the particular initial arrangement. In the block universe picture, this means that if we could see the entire four-dimensional structure at once, the laws would describe patterns extending in both directions along the time coordinate. World lines would be laid out through the block, and the equations would be satisfied whether we traced them from early times to late or from late to early. Yet embedded within that block would be a low entropy boundary toward one side, corresponding to the smooth early universe, and higher entropy regions toward the other side. Observers made of matter in the higher entropy regions would naturally define their sense of past and future in alignment with the direction of increasing entropy. Memories, records, fossils, and traces are all associated with processes that have moved along that direction. In this sense, the arrow of time is written into the structure of the block, not by the form of the dynamical laws, but by the special choice of boundary conditions. It is a feature of how the universe is configured as a whole, not of the local rules at each point. That perspective leaves open the logical possibility of other blocks, governed by similar equations but with different boundary conditions, in which the arrow might point differently or be absent altogether. Whether such alternatives exist anywhere beyond imagination is another question, one that leads more into philosophy and speculative cosmology than into direct observation. For us, within this particular universe, the combination of a low-entropy beginning and time-symmetric laws gives rise to a world in which cups break, stars burn, galaxies form, and civilizations evolve around stars and, much later, around black holes. The distant shell we imagined near the edge of cosmic time still sits inside this block, its inhabitants tracing their own bundle of world lines in a region where entropy is much higher than it was at the start, yet still able to change a little more as they use what remains of free energy. As we let this picture settle, the block universe, the special initial state, and the thermodynamic arrow become woven together, a static four-dimensional structure in which certain directions carry increasing entropy, and within which beings like us find ourselves always moving along those directions, calling one side past and the other future, while the full architecture, from early smoothness to late complexity, remains present in the background of space-time. From the image of a block universe, where every world line lies already traced through space-time, our attention can slide towards some of the more unusual shapes that general relativity quietly allows. Shapes in which those world lines do not simply stretch from past to future, but bend around and close on themselves, forming loops that look, at least in the equations, like journeys through time. In the early exploration of Einstein's field equations, some physicists began to look for solutions that described whole universes, not just isolated stars or planets. One such family involves a kind of idealized dust, a pressureless fluid that represents matter spread throughout space. Willem Jacob van Stockham examined a solution first discussed by Cornelius Lanczos, in which this dust does not simply sit still. It rotates in a steady way around a central axis. When this rotation is woven into the geometry, space-time itself acquires a twist. Lines that would otherwise be straight geodesics in a non-rotating universe now wind around, following the swirl of the dust. In this twisted geometry, something remarkable happens. Certain time-like paths, the kind that a physical particle could follow without breaking the speed of light limit, can loop back and meet themselves. A particle that travels along one of these special world lines moves always forward in its own proper time. Yet the coordinates of space-time bring it back to an event that lies in what we would usually call its own past. These closed time-like curves exist not as shortcuts through an external timeline, but as features of the space-time structure itself, allowed by the same equations that describe more familiar gravitational fields. We can picture this as threads woven into a fabric that has been twisted so strongly that some threads circle back, re-entering regions they passed before, not in space alone, but in the combined space and time coordinates. This is not the only rotating universe that general relativity admits. Kurt Gödel, working at the Institute for Advanced Study in Princeton at the same time as Einstein, found another solution in which the entire cosmos rotates in a particular way. In Gödel's model, the distribution of matter and the form of the metric lead to a global swirl. The geometry is arranged so that, again, some time-like paths curve around and intersect their own earlier segments. There is no global surface that can be identified as the present moment for everyone. The structure resists being sliced into a single shared now. In such a universe, if we imagine following a suitable trajectory in a spaceship or along some other world line, the mathematics says that we could eventually arrive at an event in our own history. The equations themselves do not object, because at every step along the path, the motion remains subluminal and respects the local rules. It is only when we look at the entire loop that we see its unusual character. Gödel's construction is highly idealized, with a matter content and rotation very different from what we infer for our actual universe. Still, it demonstrates that closed time-like curves are not alien to general relativity. They emerge naturally from certain arrangements of mass, motion, and curvature. We do not have to stay with entire rotating universes to see space-time twist in ways that invite these questions. Even around a single rotating mass, the geometry changes. The solution, known as the Kerr metric, describes the spacetime outside a spinning black hole. In this solution, the black hole's angular momentum drags nearby inertial frames around with it, an effect called frame dragging. Close enough to the hole, there is a region where nothing can remain in place relative to distant stars. Everything is compelled to co-rotate, carried along by the twisted geometry. We can think of this as placing a spinning sphere in a thick, very flexible medium. The rotation curls the surrounding medium into a vortex. In the actual mathematical description, it is not a fluid that is turning, but the structure of spacetime itself, affecting how gyroscopes precess, how orbits precess, and how light rays thread through the region. Observations of accretion disks around black holes and measurements of precession in systems closer to home provide evidence that this dragging of frames is a real phenomenon, not just a theoretical curiosity. Within the Kerr solution, if we extend the geometry beyond the event horizon and through idealized regions where singularities and horizons take particular forms, The equations reveal corridors that connect one asymptotic region of spacetime to another. In some versions of this extended picture, paths can be traced that move from one region, pass through the interior structure of the rotating black hole solution, and emerge elsewhere, perhaps even in a region that stands in a different temporal relation to the original. Whether such extensions reflect anything realizable in nature is doubtful. Small perturbations or quantum effects would likely disrupt the ideal structure. Yet as mathematical possibilities, they show that even objects as familiar in modern astronomy as black holes can host geometries with room for highly non-trivial world lines. We can let the exact details of these extended diagrams remain indistinct, like faint lines on the edge of a map. Another family of solutions that has captured imagination is the wormhole. In the language of general relativity, a wormhole is a configuration in which two distant regions of spacetime are connected by a throat, a kind of bridge that allows a time-like path to travel from one mouth to the other more quickly than a comparable path through the surrounding space. The classic picture is to draw two distant points on a sheet of paper, then fold the sheet so the points touch and tap a hole between them. In four-dimensional spacetime, the analogy is more subtle, but the idea of a shortcut within a curved geometry is similar. Mathematically, one can write down metrics that describe such bridges. Some are ephemeral, collapsing too quickly to be traversable. Others, in principle, could remain open if the stress energy threading the throat has particular properties, including negative energy density relative to certain observers. In everyday materials and fields, energy density is positive. The requirement for negative energy suggests that traversable wormholes would need exotic matter of a kind we do not know how to assemble at macroscopic scales. Quantum field theory does allow, in specific contexts, small regions where the effective energy density dips below zero for a moment due to vacuum fluctuations and related effects, but whether these microscopic features can be organized into a stable structure of the sort needed remains unknown. If, in a thought experiment, we imagine a traversable wormhole whose two mouths are initially synchronized in time, and then we move one mouth along a path, where gravitational fields or high-speed motion cause it to age less than the other. The wormhole can link events that differ in their temporal coordinates as well as their spatial ones. A traveler entering the younger mouth could emerge from the older mouth into what appears to be the past, relative to the outside universe's chronology. The ingredients here are familiar from earlier in our journey: time dilation due to motion or gravity, and paths in space-time that are time-like and respect local causality. It is their combination within this special geometry that gives the loop-like structure. These constructions sit at the edge between mathematics and physics. On one hand, they are legitimate solutions of Einstein's equations under certain assumptions about matter and boundary conditions. On the other hand, nature may enforce additional constraints, perhaps through quantum effects, that forbid any configuration allowing closed time-like curves in a physically realizable way. Some proposals suggest that quantum fluctuations would intensify near such curves, destabilizing the geometry before a macroscopic loop could form. Others point out that the kinds of stress energy required to maintain wormholes or extreme rotating universes may violate energy conditions that hold for all known classical forms of matter. A helpful analogy is to consider engineering designs drawn on paper. We can sketch a bridge with an elegant, minimal set of supports that appears to span a huge distance. The equations of static equilibrium might say that, in an ideal material with infinite strength, the structure would hold. But when we ask whether any real material can achieve those properties, we find limits that prevent construction. In a similar way, general relativity may permit space-time geometries that cannot be realized with the actual fields and particles available in our universe, at least not in stable, macroscopic form. For the imagined civilization living on a shell around a black hole, all of this would be part of the conceptual terrain. They might understand the equations for rotating universes and wormholes as well as we do. They would know that time passes at different rates for paths at different gravitational potentials and with different motions. And they might even speculate about shaping space-time to create shortcuts. Yet their practical engineering would still be bound by the same questions. whether the necessary energy densities can be achieved, whether quantum effects support or undermine the classical picture, and whether the larger structure of their universe allows such configurations at all. We can picture them standing near the inner surface of their shell, watching the black hole's spin drag nearby space-time into slow procession, aware that the same theory that explains their clock rates and orbital mechanics also contains these more elaborate possibilities. For them, as for us, time travel in the sense of closed time-like curves might remain a feature of equations on charts and displays, rather than a technology they can deploy. The presence of these exotic solutions, however, tells us something important about general relativity itself. It is a theory rich enough to accommodate not only smooth expansions and simple orbits, but also twisted, multiply-connected geometries in which the ordering of events can become intricate. That richness hints that the complete story of space and time, especially when quantum effects are included, may involve structures that go beyond simple curves and surfaces, perhaps with space-time emerging from more fundamental ingredients that explain why some solutions are realized and others are only shadows on the edge of possibility. To understand what space-time might really be, we can let our focus drift away from galaxies, black holes, and the large-scale arc of the cosmos, and instead move inward toward the very small, into a domain where particles behave like waves, and uncertainty is part of the description, and where one equation written in the early 20th century began to weave relativity and quantum theory into a single thread. In this smaller world, electrons are no longer tiny marbles circling a nucleus. They are excitations of a field, spread out, with properties that include not only mass and charge, but also an internal kind of angular momentum called spin. Paul Dirac set himself a precise task: to write down an equation that would describe electrons in a way that respects special relativity, so that energy and momentum fit consistently into the geometry Minkowski had introduced. When he solved that problem, the result was the Dirac equation, a relation that links space-time derivatives of a field with matrices encoding spin and other internal structure. A curious feature of the equation is that, like taking a square root, it comes with more than one branch. When we take the square root of one, we get both +1 and -1. In a similar way, the Dirac equation contains solutions that correspond not only to the familiar electron, but also to states with the same mass and opposite charge. At first, these negative energy solutions were puzzling, but Dirac interpreted them as signaling the existence of a partner particle, the positron, which would later be observed in cosmic rays and in laboratory experiments. Matter and antimatter appeared side by side in the mathematics before they were fully recognized in the data. In this sense, the Dirac equation was the first clear meeting point of relativistic spacetime and quantum mechanics at the level of a single particle. It showed that when we allow fields to live on Minkowski space and insist that their dynamics respect the symmetries of that flat spacetime, we gain a remarkably accurate description of electrons, their magnetic moments, and their behavior in electromagnetic fields. From there, the picture expanded into quantum field theory. Instead of treating particles as primary, we treat fields as the fundamental entities. Electron fields, quark fields, photon fields, and so on, each filling spacetime and capable of being excited in quantized amounts. The vacuum is no longer an empty stage, but a state in which all these fields sit in their lowest energy configuration, fluctuating quietly. Creation and annihilation operators replace simple wave functions, and interactions become processes in which quanta are exchanged. In this framework, spacetime, specifically the flat spacetime of special relativity, acts as a fixed background. The metric is set to that of Minkowski space, with its light cones and invariant intervals, and the quantum fields live and evolve on that stage. Calculations of scattering amplitudes, of the behavior of electrons in electromagnetic fields, and of the forces that act at very small distances, all rely on this combination. Quantum operators defined over a smooth, continuous spacetime. When renormalization techniques are applied, infinities that appear in intermediate steps can be tamed, leading to predictions that match experiment with extraordinary precision. We can picture this as a quiet arena, the flat fabric of space-time extending in all directions. While on it, the quantum fields shimmer and interact like overlapping patterns on a surface. When we try to bring gravity fully into this picture, the role of space-time begins to shift. General relativity tells us that space-time is not fixed and flat, but curved and dynamic, responding to energy and momentum. If we attempt to simply place quantum fields on a curved background, treating the geometry as given, we can study useful situations. Particle creation in expanding universes. Hawking radiation near black holes. The way horizons affect quantum fluctuations. But if we attempt to promote the gravitational field itself to a quantum operator in the same way as other fields, new infinities arise that do not submit easily to the same renormalization strategies. The idea of a fixed stage with quantum actors starts to feel incomplete, because in Einstein's picture, the stage is one of the actors too. This tension has led to different attempts at a deeper unification. One of them is string theory, and its later extension, M theory. In these approaches, the basic entities are not point-like particles, but one-dimensional strings or higher-dimensional objects that vibrate. Different modes of vibration correspond to different particle species. One pattern behaves like a graviton, another like a photon, others like quarks and leptons. To make the equations consistent and free of certain anomalies, the theory often requires more than 4 dimensions of space-time, 10, 11, or in some formulations even more. The extra spatial dimensions are thought to be compactified, curled up at scales so small that they are not directly accessible at current energies. We might imagine an instrument with many strings, some extended along familiar directions, others tightly wound around loops too small to see. The tones that arise from this instrument are the particles and forces we observe, each note linked to a particular vibration in the deeper structure. In many versions, space-time itself is part of this structure. Its shape and size arise from the configuration of the strings and branes, and changes in geometry correspond to changes in the state of the underlying theory. In that sense, space-time is not entirely separate from the entities that move within it. Even so, in many practical calculations, a background space-time is still assumed, and the strings vibrate within that context. The theory is mathematically rich and has produced insights into black hole entropy, dualities between different descriptions, and holographic correspondences. Yet direct experimental signatures remain elusive. For our quiet exploration, it is enough to note that string theory offers a picture in which space-time is extended, multi-layered, and perhaps integrated into a larger framework, but it does not yet answer in a final way what space-time is made of. Another line of thought takes a different starting point. Loop quantum gravity sets out from general relativity itself and attempts to quantize the geometry directly, without introducing strings or extra dimensions. In this approach, the smooth continuum of space-time is replaced, at the smallest scales, by a network of discrete elements. Areas and volumes are not continuous quantities, but come in tiny, quantized units. The gravitational field is represented by spin networks, graphs whose edges and nodes carry labels corresponding to quantum numbers of geometry. As these networks evolve, they trace out structures called spin foams, which can be thought of as histories of quantum geometry. The image here is that of a lattice or web, not regular like a crystal, but more like an intricate mesh, where each link carries information about how neighboring regions of space are related. At scales near the Planck length, space-time in this picture is granular, and the continuum metric we use in classical general relativity emerges only when we look from far enough away, averaging over many quanta. Length, area, and volume become derived. Macroscopic notions, similar in spirit to how temperature and pressure arise from the collective behavior of many molecules. Both string theory and loop quantum gravity, in their different ways, suggest that our familiar space-time may be a large-scale description of something more basic. One starts with extended objects vibrating in a higher dimensional setting. The other starts with quantum versions of the very connections that define geometry. Each offers tools for understanding some aspects of black holes, early universe cosmology, and quantum fields in curved backgrounds. Each has open questions and technical challenges. We can let them stand side by side, like two sketches of a landscape drawn from different vantage points. A common thread, hinted at in various proposals, is that space-time might not be fundamental at all, but an emergent structure arising from underlying degrees of freedom that are, in some sense, informational. Correlations in quantum states, entanglement patterns, and the counting of microstates in certain gravitational systems all point toward the possibility that distance, duration, and curvature could be derived concepts, capturing how information is arranged and connected. In that view, asking what space-time is made of may be a little like asking what temperature is made of. The answer lies not in a new substance, but in the behavior of many smaller constituents taken together. For the distant civilization around the lonely black hole, this would mean that the space-time they so skillfully navigate, the curved region they use to stretch their own time, the expanding background whose redshift they measure in arriving photons, could itself be a large-scale summary of something deeper. They might already suspect that their equations are effective descriptions rather than final ones, that their coordinates and metrics are tools for organizing experience rather than the last word on reality's architecture. Around them, the expanding fabric of the universe continues to carry distant galaxies away. The deep infrared glow of the cosmic microwave background still falls softly on their detectors, shifted by the growth of space. Nearby, regions where space-time curves strongly around mass guide the paths of light and matter into loops and spirals. Beneath all of that, according to these quantum visions, there could be patterns more microscopic than any instrument can resolve, patterns that give rise to the geometry they inhabit, in the same way that individual crossings in a woven cloth give rise to a smooth surface when seen from afar. As we stay with this idea, the search for a unified theory becomes less about adding one more layer of equations and more about finding the right description of those underlying patterns from which both quantum fields and space-time itself might arise. The details remain open. The candidates varied. But the direction of questioning leads toward a picture in which the stage and the actors, the fields and the geometry, and perhaps even the flow of time, are all facets of a deeper, shared structure that we are only beginning to outline in our thoughts. After many attempts to treat space and time as the basic stage on which everything else unfolds, a different possibility begins to take shape. One that suggests the stage itself might be woven from something deeper, while far away in the future, a patient civilization around a solitary black hole continues its work under a sky that grows thinner and more subdued. We can let our thoughts return for a moment to the old debate between Newton and Leibniz, now seen with Einstein's equations in the background. Newton imagined absolute space and absolute time as a fixed arena, an unchanging scaffold within which planets move and forces act. Leibniz preferred to think in terms of relations, insisting that what is real are the distances and intervals between things, not a separate container in which they sit. With general relativity, Einstein brought these viewpoints into a new arrangement. Space-time became geometric, able to curve, stretch, and ripple. At the same time, it remained relational, because its curvature is tied to the distribution of matter and energy, and the motion of matter and energy responds to that curvature. In a compact phrase, matter tells space-time how to curve, and space-time tells matter how to move. Neither side is truly independent. From here, it is not a large step to imagine that even this interdependence might itself be part of a wider structure. Perhaps the geometry we call space-time is a summary of more basic connections, the way a map summarizes the relationships between many locations, without being the territory itself. One line of evidence pointing in that direction comes from the idea of holography. Juan Maldacena's work in the late 1990s hinted that a theory of gravity in a particular curved space-time, called anti-de Sitter space, can be exactly equivalent to a quantum field theory defined on its boundary, a region with one fewer spatial dimension and no explicit gravity. In this correspondence, often shortened to AD-SCFT, every process in the bulk spacetime has a mirrored description in the boundary theory, and every correlation on the boundary has a counterpart in the interior geometry. The image often used is that of a hologram, a two-dimensional surface that encodes a three-dimensional scene, so that when it is illuminated in the right way, the full depth appears. Here, the analogy is more abstract, but the suggestion is similar. The distances and angles inside the gravitational spacetime can be read from patterns of entanglement, energy, and correlation in the lower dimensional theory. In some modern interpretations, the geometry of spacetime is not merely a backdrop for the boundary degrees of freedom. It is a convenient way of summarizing how those degrees of freedom are organized. The notion of inside and outside, of near and far, may be re-expressed as statements about how strongly different parts of the boundary theory are connected. A thought can rest there for a moment, hovering between surface and volume. If spacetime can emerge from correlations, it becomes natural to ask what happens at the smallest scales. Many approaches to quantum gravity, even when they differ in technical details, hint that continuity may break down near the Planck length and Planck time. Below those scales, it may no longer make sense to talk about arbitrarily small intervals of distance and duration. Instead of a smooth continuum, there might be discrete units, like grains in a very fine sand, or nodes in a vast network. From far away, a beach looks like a featureless strip along the shoreline. Only up close do individual grains become visible, each with its own shape and position. In a similar way, the smooth curves of spacetime used in general relativity may be the large-scale appearance of a structure built from smaller elements. In loop quantum gravity, for example, areas and volumes come in quantized units, and space is described by spin networks, graphs whose links and nodes carry labels corresponding to quantum states of geometry. The continuum metric is recovered statistically, by averaging over many such quanta. What we call curvature becomes a collective property of how these building blocks are arranged. If this picture is roughly right, then many attributes we ascribe to space continuity, dimensionality, even the idea of a straight line, are not fundamental ingredients. They are emergent regularities, stable enough at large scales to be treated as if they were basic, in the same way that the surface of the sea can be treated as smooth for the purpose of navigation, even though it is, at another level, made of countless molecules in motion. The idea that something familiar can emerge from many lower-level elements is not foreign to us. Our own bodies provide an example. A human brain is composed of neurons, themselves made of cells, which are built from molecules, which in turn are arrangements of atoms and subatomic particles. None of these individual components, taken alone, is conscious. Awareness arises from patterns of activity in vast networks of neurons, shaped by experience and interaction. We accept that properties like memory or mood are not separate substances. They are features of complex configurations. Temperature offers another analogy. A gas has a temperature, but temperature is not an extra particle mixed in with the rest. It is a measure of average kinetic energy, a summary of how fast molecules move on average. At the level of a single molecule, temperature does not exist. It only becomes meaningful when many molecules are considered together. If we extend these analogies, concepts like now, before, after, and distance could be understood in a similar spirit, not as additional ingredients of reality, but as patterns in a deeper structure, perhaps one based on quantum information and correlation. Spacetime would then be an emergent arena, appearing whenever a large number of microscopic degrees of freedom settle into configurations that support such an interpretation. The fact that we can measure intervals and curvature with great precision would not contradict this. It would simply mean that the emergent description is robust on the scales we inhabit. We can bring this thought back to ourselves, sitting within a vast universe. Our sense of having a present moment, anchored in a particular body at a particular place, might be intertwined with the way our brains process information, using memories of earlier states and predictions of later ones. In that sense, subjective time is already emergent from neural activity. Extending the idea outward, cosmic time and cosmic distance might be emergent from still deeper levels that we glimpse only indirectly through theories like holography and quantum geometry. Far ahead, in the imagined future, where the universe has cooled and expanded for untold epochs, the civilization around the lonely black hole may have come to similar conclusions. In their libraries and data vaults, they might keep refined versions of our current theories, extended and corrected by the discoveries of many eras. They would know that time passes at different rates depending on gravity and motion, and they would rely on that fact to stretch their existence by orbiting close to their black hole, where clocks tick more slowly relative to the sparse, distant cosmos. They would understand that the universe expands, and that distant galaxies continue to drift away as space grows, carrying most of the original matter content beyond their observational horizon. Around their shell, regions where space-time curves strongly around mass shape the trajectories of light and matter. The deep infrared glow of the cosmic microwave background, dimmed and stretched by the continuing expansion, still arrives as a faint murmur, a reminder of the early plasma from which structure first emerged. The black hole at the center gradually loses mass through quantum processes, radiating at a rate that increases as it shrinks. For that civilization, each quantum of energy extracted from the surroundings becomes precious, used to maintain habitats, instruments, and archives as long as possible. They have learned to read space-time like a text, to predict gravitational waves rippling through the fabric, to measure tiny changes in the paths of pulsars and the shapes of distant galaxies. Yet even for them, questions remain. If space-time is emergent, from what does it emerge exactly? Are the underlying degrees of freedom best described as strings, as spin networks, as something more abstract, like algebraic relations or patterns of entanglement? How many different emergent spacetimes are possible, and why did their universe take the form it did? There may be proposals, competing frameworks, careful derivations, and elegant correspondences. Much as we have begun to see, there may be partial answers that work in certain regimes. Near black hole horizons, in the early universe, in regions of high symmetry. But as their black hole slowly evaporates, the practical questions of energy and duration press quietly against the theoretical ones. They can delay, redirect, and optimize, arranging their world lines in space-time to experience more moments than a similar civilization in a milder gravitational field. They cannot, however, halt the increase of entropy altogether, or stop the broader trend toward equilibrium in the universe beyond their shell. In this way, they become a kind of mirror for us. No matter how refined their understanding of emergent spacetime becomes, they remain inside the structure they are trying to describe. They cannot step outside the universe to inspect its foundations from the outside in. Their best theories, like ours, are patterns drawn within the block they inhabit, relating one part of the structure to another. We can picture them near the end, their instruments still turned toward the thinning sky, watching the last phases of their black hole as its mass dwindles and its radiation changes. The shell that once orbited in a strong gravitational field now surrounds an object that is lighter and warmer, until even that final anchor of curvature fades. Their world lines, woven so carefully around this center, eventually drift into a region where usable energy is scarce, and the patterns of activity that support their civilization become sparse. What remains, in the language of emergent spacetime, is a geometry that has carried them as far as it can. Somewhere within that geometry, in the relations between fields, quanta, and whatever deeper entities may exist, the full story of space and time is encoded. Whether any finite intelligence can ever extract that story completely is unclear. Perhaps the nature of space-time, like the interior of their own consciousness, is something that can be approached in layers, each theory revealing a little more structure without ever reaching a final, simple core. As the universe continues along its path, from early low entropy to later stages of greater uniformity, the idea that space and time themselves might be emergent becomes part of the tapestry, one more pattern within the larger whole, traced by world lines that include philosophers, scientists, distant engineers around a black hole, and all the quiet observers who, for a while, look up at the sky and wonder what it means to live inside a structure that may be more like a story than a stage. Together, we have gently passed through the great ideas of space and time, from the ways ancient people imagined the cosmos to scientific discoveries showing that time can stretch, slow down, and is far from absolute. Through this journey, the universe appears not as a silent stage, but as a living structure, where light, matter, and time itself are woven into a story spanning billions of years. The message that remains is not found in formulas or data, but in humility before a reality far greater than our everyday experience. Thank you for spending this moment listening, resting, and reflecting with the channel. Your quiet presence is what allows contemplative journeys like this to continue. In the episodes ahead, we will keep exploring together new surprises and deeper secrets of the vast universe, where each new question opens onto another quiet horizon, inviting you to keep listening, to keep contemplating, and to let your mind drift gently among the stars.